the Bernoulli, the binomial, and the Poisson distributions. In each of these distributions, we look at an experiment that we do, we check the result, and we ask what is the probability that we would get some result. Let's start with the Bernoulli distribution because this one is the simplest. In this one, let's say that we do a commit to a build, a continuous deployment build, and we ask what is the chance that this commit is going to pass successfully in our continuous deployment build system. So if we looked at the chance and we know that the chance is 0.9, that this is the chance of the Bernoulli experiment. We denote x as a random variable that would receive 1 if the test is successful, if our commit passes successfully, and 0 if the test does not pass, fails. Because the continuous build system can either succeed or fail for a specific commit. It's important to note that the Bernoulli looks at a single trial, at a single experiment, at a single commit that we do to the build system. And it asks, what is the chance? Draw the distribution. We have a formula for the distribution. The distribution is, and because it's a single experiment, a single commit, then we know that the probability of getting a 1, which is success, the probability that the random variable, we name it, that we have x, the probability of x equals 1 is going to have 0.9 because this is the probability of getting a success through the build system. What is the probability of getting a failure through the build system? 0.1. And when we have such a model of the distribution, then we also have pretty much automatically, all the way the minor calculation, the standard variation, the expected value, etc. The expected value is simply going to be P, which is the probability. So this is the Bernoulli distribution. This is the Bernoulli random variable. We say that the random variable is following the Bernoulli distribution, a single trial. The expected value is P. The probability that we have success is P. This is the parameter. P is the only parameter to the Bernoulli distribution which we need to plug in. The binomial is like a Bernoulli but multiple times. So now instead of 1 commit to the build system and we ask how many successes we're going to have, we do 10 commits. And we ask how many of these 10 commits are going to be success. This is the binomial distribution. This is the binomial random variable which follows a binomial distribution. In this case, we ask what is the probability that we are going to have 6 successes. So it may look like 6 successes is going to be the Bernoulli multiplied by itself, 0.9 times 0.9 times 0.9 times 0, 6 times. It may look like this. However, because we don't care in this case which of the 10 builds are going to be successful. It could be 1, 2, 3, 4, 5, 6. It could be 5, 6, 7, 8, 9, 10. And it could be 1 and 6 and 6 and 1. Therefore, we need to plug into the distribution of the binomial distribution also the n choose k, meaning we need to time it by n choose k. If we ask about the expected value of the binomial distribution, then it's simply, let's say we do 10 builds and the probability for each build to be successful is 0.9, then the expected value is n times p. 10 times 0.9, which is 9. We expect 9 builds to be successful. And this is also the mean. So we had the Bernoulli distribution, which is a single experiment. The only variable is p. The only input variable to this function is p. What is the probability that we're going to have success in this experiment? We had the binomial distribution with 2 input parameters, One is what is the Bernoulli probability for a single experiment, and the second one is how many experiments do we run? 10 builds, 2 input variables. Poisson is asking a different question. Poisson is asking, we have a time interval. We have 10 minutes, or let's say we have 2 hours. What is the probability that we are going to have 8 builds in these 2 hours? And the Poisson distribution accepts a single parameter named lambda, which for this same time interval is telling us what is the probability, actually how many successes or how many observations did we have during these 2 hours. So if lambda is, this is the only parameter to the Poisson, if lambda is 6, this means we observed 6 commits during these 2 hours. And now we can ask, what is the probability that during some other 2 hours we are going to receive 8 commits? And then we have this formula with e to the minus lambda, etc. That is the probability distribution for the Poisson. The only parameter is the lambda, how many we observed for a specific time interval. For 2 hours of running builds, we observed 6 commits, and now we ask about 8 what is the probability that we are going to have 8 commits? If we are given 6 as lambda, we know that we are used to observe 6 commits during 2 hours, and now we ask about 8. We plug into the lambda the number 6, and because this is the only parameter, with this we could deduce the probability of additional excess.